Taxonomy of Dynamic Systems, Arrow 320, Introduction to Dynamics and Control. In this tutorial, we're going to take a look at a way of classifying the types of dynamic systems that we will be using throughout the quarter. These systems are described with differential equations. There are fundamentally three different ways of looking at control systems and dynamic systems. And we're going to go ahead and start with the first way of looking at things that we're all very used to, which is the continuous time dynamic systems. So these are systems that are dynamic in nature, so they involve forces and moments, and they use continuous time variables, and that really is the world that we're used to, right? We're used to things that happen in a continuous way, and that really comes from the notion of Newtonian physics and Newtonian dynamics. We can break this world up into four different parts that do have intersections, as indicated by the diagram. And so the first thing that we would look at is what we would refer to as the linear or L systems. Now, the reason this is the first thing we look at is because it's actually one of the easier for us to analyze. It's not necessarily always an accurate representation of the physical world, but it is the type of system where we can do the most generalized analysis. And we're used to dealing with these kinds of systems. You've seen these in your math classes and in your physics classes. And it's how we model the world when we do sum of forces and whatnot. But linear systems have to obey two principles. They have to obey the principle or law of superposition, which means that if I operate on the sum of two variables, that's the same as operating on the variables independently and then adding them together. So I can superimpose solutions, right? We're used to doing that when we solve differential equations. We superimpose the homogeneous solution with the particular solution. And that is represented by this equation here, that f of x plus y equals f of x plus f of y. The second principle that linear systems have to obey is the idea of homogeneity. And that means that if I multiply a variable by a constant and then operate on it, so a times x, and then operate on it with f, that's the same as taking a times f operating on x. So this is essentially the same idea as a linear polynomial, right, where you have constant slope, or a linear equation. But this works for other operators like differential operators as well. And so from a differential equation point of view, this equation down here really represents kind of a generalized way of looking at linear differential equations. And the key to identifying linear differential equations is that there are no products of y or its derivatives. So I have no y times y or y times y dot. That's in this case down here for this differential equation. You would never see it. The minute you have a product of the variable you're trying to solve for here, so y, with itself or its derivatives, then that would be considered, that would not be a linear system. So what kind of system would you have? Well, you would have a nonlinear system. So a nonlinear system really is a broader class of systems which really contains all of the linear systems. But the nonlinear systems, here drawn separately, represent any kind of system that may have products of the thing we're taking the derivative of, say x here. So this equation right here is what's called a van der Pol oscillator, V-A-N-D-E-R-P-O-L, if you want to look it up, 3 different words, van der Pol oscillator. And notice it looks basically like an oscillator, except for this damping term here. Mu is a constant in this case. This damping term is proportional to x squared, and x is the variable that we would be solving for in this differential equation. So I've got x times itself giving me x squared times the derivative of x. So I've got a nonlinearity in this term right here. And this would violate the principle of superposition and homogeneity. Another type of common nonlinearity we can run into, which is something we saw the other day, is that I can have a function or an operator applied to the variable which I would be solving for. So this equation down here represents the solution, represents the motion for a pendulum. And to model it properly, we would use the sine of the angle, here u, but we linearized that, right, by assuming that the angle was small and that the sine of theta was approximately theta, or sine of u is approximately u. So we can linearize equations, which is something that you will learn about at some point down the road. So the nonlinear systems will be these N or NL systems. And then finally we can look at, well, this idea of time varying. And it's not that the system itself is varying, doesn't evolve over time, right? All dynamic systems evolve over time. What we're really asking is, do the coefficients of the variable y themselves vary in time? And so that's what we would mean by a time varying system, is, say, for example, the stiffness coefficient could vary over time. All right, not just it's so the spring coefficient could vary in time, or the damping coefficient could vary in time, or the mass of the system could vary in time. And that's represented here by this generalized form of a nonlinear system where these Pn and Pn minus 1 and so on are coefficients of the variable y that we're going to solve for in the differential equation, and here are its higher derivatives. But notice they're functions of x, which is the time-like variable for this representation of the differential equation. So that would be a time-varying system. Finally, we could have a time-invariant system, which is where you have constant coefficients. So the coefficients don't vary in time. But notice y, in this case, the variable that we would be solving for in the differential equation, is a function of time, but the coefficients that multiply y and all its derivatives are not functions of time. And so we're going to constrain ourselves mostly to linear time invariant systems, or LTI. This is the type of system that is easiest for us to deal with initially. We can apply some very powerful solution techniques to that, to these kinds of systems, which we can't apply to others. And because we've really developed such a specific class of systems, these linear time invariant systems, we can solve, when we solve one, we'll know how to solve almost all of them. So again, the linear time invariant, or LTI systems, is where we'll concern, where we're going to spend most of our time on in the class. But of course, we could have nonlinear time invariant, or we could have nonlinear time varying, or we could have linear time varying systems. All of those would be valid representations of the system, some more difficult to analyze than others. So that's the continuous time world, and another way of looking at the world would be what we would refer to as the discrete time dynamic systems, or discrete time world. And there's transformation involved, and you can go back and forth between continuous and discrete time systems. We're not going to spend a lot of time on discrete time systems here because most of the dynamic systems we deal with are continuous in nature. But these are systems that are really, it's really a digital representation of the system. So using a computer to control a system would get it to discrete time control. And in these cases, there's a fixed and finite time interval that we're using to analyze the system in. So in other words, variables evolved in fixed and finite time intervals. Whereas in continuous time, the variables evolve in infinitely small intervals of time. In addition to the ways of classifying dynamic systems we looked at in this video, there are also other attributes of dynamic systems we can use to classify the systems which you are already familiar with. Systems can be classified by the order of the highest derivative in the system of equations. The systems can be homogeneous or non-homogeneous. As we will see, this classification is equivalent to an unforced or forced system. Systems of differential equations can also be coupled or not. If a system is coupled, the different differential equations depend on one another in some way and can only be solved simultaneously. It is generally useful to classify dynamic systems because some systems have nice analytical solutions, others do not. For most of this course, when we analytically solve dynamic systems, we will stick to linear time invariant, or LTI systems. For those dynamic systems which are nonlinear, we will use a numeric solver such as Rumkutta or the MATLAB function ODE45.